Imagine I ask, what is the chance that a person carries an umbrella? You might look at everyone in a plaza and count the umbrellas. But then I add two words, given rain. Those two words change the world we are counting inside. People standing in sunshine are no longer relevant. Conditional probability is simply probability after a filter. First, keep the cases that match the condition, then calculate the chance inside that smaller world. In this video, we will build that idea with pictures before touching the formula. Start with 100 commuters. Every dot is one person, so the whole board is our original world. 30 people are traveling on a rainy day. We color those 30 dots blue. That blue group is the condition, rain. Now look for umbrellas. 24 of the rainy day commuters carry one. Another 14 carry umbrellas on dry days. So there are 38 umbrellas in the full group. If we ignored the condition, the ordinary probability of an umbrella would be 38 out of 100. That number is correct for a random commuter, but it answers the wrong question once we hear given rain. Now apply the rain filter. The 70 dry day dots fade away. Nothing mysterious happened to them. They simply fail the condition. Our active world now contains only 30 rainy day commuters. This is the important reset. The denominator is no longer 100. It is 30, because 30 cases survived the filter. Among those 30 survivors, 24 carry umbrellas, so the conditional chance is 24 out of 30, or 80%. Filter first, then count inside what remains. Now the formula has something visible to describe. Let A mean carries an umbrella, and let B mean rainy day. The condition B becomes our new denominator, the size of the blue world. The numerator must satisfy both ideas at once, umbrella and rain. That overlap is called A intersect B. So probability of A given B equals probability of A and B divided by probability of B. The vertical bar is best read as after filtering by. It is not decoration, and it does not mean divide. The division appears because we are rescaling the filtered world to one whole. Let us try the same move with a deck of cards. Question: what is the chance of drawing a queen, given that the card is a face card? Before the condition, the deck has 52 possible cards, but given face card tells us to keep only jacks, queens, and kings. There are 12 face cards, so 12 becomes the new denominator. 4 of those 12 are queens. The answer is 4/12, which simplifies to 1/3. A common mistake is 4 over 52. That would answer the chance of a queen before learning anything about the card. New information removes possibilities, and the denominator must shrink with them. Notice that we never needed to memorize a special card trick. We only kept the face cards, then counted queens inside that set. Conditional probability becomes especially useful when two directions sound similar. Suppose 1,000 people take a screening test. 10 actually have a condition, and 9 of those 10 test positive. Among the 990 people without the condition, about 50 also test positive. Now compare two questions. First, what is the chance of a positive test given the condition? We filter to the 10 people with the condition, then see 9 positives. That is 90%. Second, what is the chance of the condition given a positive test? This time we filter to everyone who tested positive. There are 59 of them, 9 true positives and 50 false positives. Only 9 of those 59 actually have the condition, about 15%. The same two labels appear, but reversing the condition changes the filtered world, so it changes the answer. That 15% can feel surprising, so look at the picture instead of arguing with the number. The test catches 9 of the 10 real cases, which is genuinely strong. But the group without the condition is enormous, 990 people. Even a fairly small false positive rate creates 50 false alarms there. After we filter to positive tests, those 50 false alarms share the room with only 9 true positives. This is the base rate effect. A rare condition begins with a tiny group, so the larger background group can dominate the positive results. The visual habit is powerful. Draw actual counts, then filter. Percentages alone often hide which group is large. There are two other pictures that tell the same story. A tree diagram filters by following a branch. Begin with everyone, take the positive test branch, and then compare the two kinds of people that arrive there. An area diagram filters by cropping the canvas. Keep the positive strip, enlarge it, and ask what fraction belongs to real cases. Tree, area, and dot grid are not different rules. They are different camera angles on the same operation. Choose the view that makes the surviving group easiest to see. For beginners, actual count dots are often the clearest because every person stays visible. The filter idea also explains 3 useful special cases. First, independence. If learning B does not change the proportion of A, then filtering by B leaves the chance of A unchanged. For example, if 80% carry umbrellas both inside and outside the rain group, rain provides no information about umbrella carrying in this made-up world. Second, an impossible overlap. If no surviving B case is also A, then the conditional probability is 0. Third, certainty inside the filter. If every surviving B case is A, the conditional probability is 1. 0 means none of the filtered cases qualify. 1 means all of them qualify. Everything else is the fraction in between. When a conditional probability problem feels confusing, check 3 things. 1. Did you filter using the words after given? In a given B, B chooses the new world. 2. Did you count the overlap in the numerator? The successful cases must be both A and B, not merely A somewhere in the original world. 3. Did you reverse the question? A given B usually differs from B given A because the 2 filters keep different groups. One more technical note, the condition must have a non-zero probability. If no cases survive the filter, there is no smaller world in which to calculate a fraction, so the usual conditional probability is undefined. Let us pause for one quick prediction. A school club has 60 students. 24 play music, 30 play a sport, and 18 do both. What is the probability that a student plays a sport, given that the student plays music? Freeze the numbers for a moment and choose the denominator. Given music means the 24 musicians are the only students left in the room. 18 of those musicians also play a sport, so the answer is 18 over 24, or 75%. Now reverse the words. Music, given sport. The overlap is still 18, but the filter now keeps 30 athletes. The answer becomes 18 over 30, or 60%. Same overlap, different filtered world, different denominator. If you got both, you are already thinking conditionally. If not, draw 2 circles, cover everything outside the condition, and try again. The picture will tell you which total belongs underneath the fraction. Here is the whole idea in one mental move. Start wide, highlight the condition, fade everything else, then ask what fraction of the survivors also match the event you care about. That fraction is the conditional probability. The formula is a compact record of the picture, overlap divided by condition. So whenever you see given, do not rush to divide numbers. First decide which cases are still in the room. Filter first, then calculate.